Okay, you can start now.
Okay, my paper is learning linear attention in polynomial time. Learning linear attention in polynomial time. Okay. Just at the first, we'll start with some basics and we'll go up gradually. Okay. Now, as we know, the linear regression, there are two ways to train a linear regression model. First way is using gradient descent, and as we know, there is mean squared error, and this is the equation. And we start with the slope and the bias, like as we know, and then we do backpropagation. We know the effect of every weight parameter, and then we still train it until we get the best fit. Okay, this is one way. Second way is using the normal equation, like using the normal equation we do differentiation to the mean squared error. We get the gradient, and then we equate it to 0 to get the global minimum to go to the solution direct without any training. And this is the normal equation, and in just one step we get the best. This is the other way. Okay, what will we use, or what are we going to use from these two ways with the attention? Like normal equation and gradient descent. Gradient descent did this, like the error is still decreasing until we reach the global minimum. Okay. Okay, and the normal equation just that. So we'll start also with an idea from the paper. Attention is all you need, which is attention. And firstly, we'll do tokenization and embedding to the data set. Tokenization, which you change you are converting every word to a number, and this is a type of tokenization. There are many types. There are many other types. And then we'll do embedding. We'll just represent every token with a vector of embedding. And at the end, each vector of embedding will be like this. Like the most common words will be near to each other. Okay. So every multi-head attention block will contain these things, and this contains a linear layer, and linear layer. Okay. And as we said, there are a number of tokens. Like here, for example, like any word, if you have n tokens, so you have n tokens. So yeah, then you will make embedding, and then the output of the embedding layer will be a matrix of n times n of embedding times n embedding, and this is a matrix. Okay, this matrix we will take 3 copies of it. First copy will name it query p and query and value. And every copy will go to a linear layer, to like a specific linear layer, to learn every matrix will learn like as it is. Will learn alone. Okay. So we said that it will be n times n embedding, and every matrix will go to a specific linear layer, and the output will be n times head size. Okay. And the head size, which is the size of every multi-head attention, and head size, like as we saw here as we see in the implementation, which is basically the size of the hidden units in a neural network. So the attention, like briefly, if you have a word, if you have a sentence book that read today was good, great, and you have 6. Which is number of tokens times head size, will do matrix multiplied by the same matrix but transposed. Okay, and you have a query and key. And query, what does the query represent? Like what am I looking for? This is a query. And the key, what do I have? For example, we get this. If you have a query book, and the query represents what am I looking for? So if you have a book in your hand and you have some keys, and the keys represent what do I contain? Okay, so you have a book. So you have a book in your hand. In order to understand the word book itself, is that important for you? No, it's not important, because book as itself is understood. But when we come to that, if you have that in your hand, is it important to look at book yeah, it's important because without book you will never understand that. So it's like letting the tokens talk to each other in order to, this is attention. You're letting all tokens to talk to each other. So as we said, the query is what do I looking for? What am I looking for? And the key, what do I contain? And if this is the values or the information that do I contain, the value represents here are the values or here are the information. So we make matrix multiplication again in order to get the n tokens times the head size. Like these are the dimensions as exactly as the input, which was also n times the head size. So we get the specific dimensions. Okay. What did we do right now? This equation, the query times k transpose, which is this is query. This is k transpose with, and this k transpose and matrix multiplied with the value. And the softmax, like it's just like normalizing, and this also like normalizing. And softmax only output like probability. Okay, there are two ways we will get the information from the linear regression or the idea. There are two ways to train this attention model, using gradient descent or normal equation. Okay, if you use the gradient descent, okay, we'll decrease the loss. But there is a problem with that. What is the problem? This graph maybe this only this. Why? Because of the softmax. The softmax contains many complexities. Like for example, there are exponentials. The exponential in the softmax function. So this give an impact of many complexities in the graph. So therefore, like it's not guaranteed at all when you train a gradient, when you train a model with gradient descent. It's not guaranteed at all that you will reach always the global minimum. You may reach only the local minimum. So, and this is like they call in the paper non-convex landscape or non-convex landscape. And the other way, which will use something like normal equation, like the linear regression, and they call this relaxed linear attention or convex landscape. Like it's like we will get the result only with a math in a math equation without any training. Okay, so we need like an equation like the normal equation, like the linear regression, using the normal equation. Okay, so we'll start with the algorithm with the paper, which is linear attention. First, you will have our data, our input. For example, you have n equal to 5 and equal to 5 tokens. So that and you will have the n tokens, and d, which is the number of embeddings or embeddings dimension. How much dimensions will you represent your token? For example, you have 5 tokens. Every token will be represented by three values, and these are the input. So the first step is the input, and the y is the target vector. Like for example, your input is book the thread today was, this is the input, and the target is good. This is the first step. The second step, okay, as we made before, we let the tokens talk to each other. Here it's similar, but they are letting the embedding values talk to each other, and they are called it cubic interactions. They are called it or fixed or extract feature. So they are doing cubic interactions between every three embedding values. And this like these brackets means like they are dot product and then multiplied by. Okay, then we'll get this matrix. So this is the second step. To let the tokens or the embeddings talk to each other. So the third and fourth, fifth step. So we got this in the second. So this is the third, fourth step, and fifth step. Okay. We will make exactly like the linear regression. Like this is the equation of the linear regression. we will like make similar like as this. For example, here's x trans x, which is the input, and y is the output. X transpose x. For example, we will get this. This is what that we made in step 2. This is exactly like this. For example, x transpose here is like x transpose. Here's x, for example, and this is only for ridge regression, for regularization. So it's not very important, but it's only regularization. And this is like the inverse of the matrix, and x transpose here, and y transpose here, and y is here, and x is here. So it's a little bit similar. So okay, so we got the matrix, we got the result matrix. They made a step called SVD, or singular value decomposition. It's like you have a result, the result, but you want to divide this result into V and Q and K, into the value and query and key, like we did before. So this is what singular value decomposition does. It's just dividing the result to a couple of matrices.
This is your 12th minute. Finishing.
Okay. And also there's another step by allowing up to d square heads, d, which is the embedding dimension. Like you are acting the all relationships between the tokens. So it's not like the normal attention. You are constraining the number of you are not constraining the number of heads, but here you are making it up to d square heads. So this is an old one, and this is a new one, which is there is only global minimum without any training. And they made a couple of experiments, but with very small numbers. And these are like the old one, and the full are the original transformer. So this is the result, and with the convex algorithm that we have now, this is a result, which is a linear line. This is a convex. Like it's at 10 power negative 16. And like as we made before, like it's a like direct equation to get at the global minimum right away. But here's the like a bottleneck, the elephant in the room. If this is solvable in polynomial time, why don't we train all models this way? Because the polynomial hides enormous constants. The runtime is 0.n times d power 4. For GPT-3, for example, the d, or the dimensions of embedding dimension, is 12,000. It's roughly 2 times 10 power 16, which is a problem. And if you multiply it by n, which is 300 billion tokens, you will get 10 power 29 operations. So if this is useless, this whole paper is useless? No, not quite. It's just a theoretical foundation, just like matrix multiplication was for centuries, until better algorithm were found. This proves a path exists. Thank you.
Very nice. It was a nice presentation. So a bit of a refresher. But it was nicely presented. So I got the impression that you thoroughly read the paper and tried to understand this.
Actually, these only maybe the first seven pages. The whole paper is 30-something pages.
Oh, wow.
The rest are maybe experiments or I don't know, certificates, but neither ChatGPT, neither Gemini, neither DeepSeek able to understand the rest. It's extremely hard.
It's extremely hard. Yeah, I can understand. So I think the paper is written by a real mathematician. So it becomes difficult to really comprehend.
And also I took and asked them. They traveled away and I stayed at home. I mean, I took a couple of days to make it.
Okay. No, but I think it was. I don't know. But what was the learning you took from this paper?
Sorry.
So what did you learn from this paper?
Okay, actually, like I have said to you, I made a YouTube playlist explaining the attention until here. I made a video or a playlist until here. So I explained the attention already. I have a YouTube playlist, but then These are news.
Where did we study in AI course? Did we cover attention?
No,
No.
Where did we cover? Till?
we didn't cover.
CNNs are.
We only reached transformer.
No, we
No,
didn't reach.
only
We would know. Okay, then.
we didn't reach the transformer. Only R and
RNNs or yeah, that's fine stuff. Simple tokens. Yeah, we reached in the final like simple tokens and how they operate.
Okay. Yeah, I think it should have been there, but I think it's already too packed. So I don't know.
Yeah,
10 minutes is very.
No. I mean about the AI course. I think this
No, I
transformer
mean,
and
in Egypt they took half what we took.
they don't have.
They took half of what we took.
They don't have what?
They took half of what we took here.
half.
They took half of the. Yeah, of course. I mean this I understand. But I mean yeah.
I mean, you changed the course completely also, right?
Yeah.
You were like, I'm not gonna teach this. Symbolic.
Okay, I thought I covered this transformer, but maybe I didn't cover. Yeah, I think this is attention is also something very. Yeah. It's not very. If you were working at that time when the attention paper came out, you would have also come up with the same idea. Because human mind works in a very similar manner. So it's really, if you are smart, a little bit smart, and like you are into the problem, then you tend to propose the same solution, and this is what it is.
That's actually, this idea is very interesting. Like you're doing like linear regression without any training, without any using of GPUs, with direct math equation. But this just a path, and
Yeah.
there are still many gaps.
Yeah, but with the current compute resource and everything, I think so. There is a numerical solution to this training.
And also, this representation is handmade 100%.
Yeah, I can see that.
We can tell actually.
It's very evident.
Presentation.
Yeah, you much better than Gamma.
I agree. But I was very short on time. to be
Listen,
honest.
yeah. So this is what I mean. So
Mine was made on Gamma, but
and the fonts was the presentations. The content of the slide was not very good, to be honest. It were too small. The font size were too small. It wasn't very clear. I like this. I don't know if you are not using Gamma properly. This is
no,
why I love
in
it.
Gamma or like in the website,
Yeah,
it
you
looks
change the font.
different than in the PowerPoint. So I exported it. I did a lot of edits, but in the PowerPoint itself, the text doesn't look the same. So I didn't have time to change every text box in the presentation to fit the size.
Yeah.
All good?
Yeah, all good.
Nice, Gamma. If I have.
Very nice.
So will we present again for the other doctor or will we present again?
I don't know. I don't even know him.
When it comes from Iran, we'll figure it out.
He's in Iran.
He's
Already?
stuck.
Oh
There's one
my
for
God.
Stephen Bird and,
Oh, will he really? Yeah. Will he really be coming?
Probably not.
who knows?
It seems difficult.
I believe that.
Okay, this I didn't know that he is in Iran.
Yeah, but they don't have evidence and don't mention.
I don't know.
It's like for
Okay.